All right, I think we'll get started. First of all, welcome everyone to the SNAPP seminar. It's our great pleasure to have Adam Wierman presenting today. Adam is a professor in the Department of Computing and Mathematical Science at Caltech. He joined Caltech in 2007 after receiving his PhD in computer science from Carnegie Mellon University. Adam's research strives to make the networked systems that govern our world sustainable and resilient. He's best known for his work spearheading the design of algorithms for sustainable data centers and his co-authored book on the fundamentals of habitats. He's a recipient of numerous awards, including the ACM Sigmatrix Rising Star Award, the ACM Sigmatrix Test of Time Award, the IEEE Communication Society William R. Bennett Prize, multiple teaching awards, and various best paper awards. Without further ado, I'll let you get started, Adam.
Perfect. Thank you. It's really a pleasure to be here, and although I don't see everybody's faces, it's great to see so many familiar names in the chat. So I really encourage everybody to chime in and unmute and ask questions as we go along. Makes it more fun and engaging for everybody, I think. As we all know, in this virtual seminar format, engagement breaks things up quite a bit. So yeah, so please jump in whenever you have questions or comments. I'll be happy to hear them. So this talk today is not a super technical talk, but it's a talk about a new style of analysis and result that we've been working on in our group and with a couple of people I see on the chat here as well, including Mohammed, over the last year or two. And it's something that I'm really excited about. And so my goal here is actually to introduce the type of work, the type of results that we've been going after, and hopefully motivate you to think about how you can ask the same questions in your models going forward. And so this is joint work with a few students at Caltech, Nico, Tinashe, and Tongshin, and then some collaborators at Georgia Tech as well. So jumping in, so the motivation for this work is that, as we all know, there's broad excitement about the potential for AI in terms of its use for the control of network systems, smart transportation, smart grid, smart data center design, energy efficient data center design, all of these things. But at the same time, there's a lot of hesitancy about whether we can really trust AI and ML tools in these safety critical systems. And this kind of hesitancy is driven by some of the, I'd call them sort of embarrassing failures of AI in these settings. And this is a little bit old example at this point, but I think it's really salient. So it's a good one to keep in mind. So the picture on the left here is a stop sign, which normally, a computer vision algorithm could recognize very well. But, with these strategically placed pieces of tape, the vision algorithm actually looks at this and thinks it's a speed limit sign. And this is, of course, a terrible thing to imagine happening as you're driving in your autonomous vehicle and it comes up to a stop sign and thinks it's a speed limit sign and speeds up and just goes right through the intersection. And so this sort of unexpected failure, unexpected behavior from these AI/ML tools is something that the systems, especially if we want to apply them in safety critical systems, have to be able to handle. And it's something that's just not limited to that kind of toy example that we see sort of embarrassing failures all over the place where these AI tools are applied in modern systems, from data center outages to smart city failures to autonomous vehicles to robotics to all of these things. And so, in sort of a succinct way, I think, in these safety critical systems, a key barrier to adoption for ML AI tools is that you can't afford to fail at scale in these systems. And one way this comes up, and I think a really common question that we get from industry partners who come to Caltech and talk to us about potentially applying work is a version of the following. So this particular quote was from an executive at Aerospace, but it's versions of this have come from lots of people where they basically come in and say, my my team has all these exciting ideas and these demos saying that I could use AI tool X to optimize my system, and I want to use it, but I need some guarantees if I'm going to be able to deploy this in the real world. So is there a way of, wrapping guarantees on top of these tools to make sure that I don't fail at scale? So this is a really driving question in industry and in all of these safety critical applications if we want to be able to apply these tools. And to make this really concrete, Anna's team at Google, Anna's a part of this applied probability community, and she runs the Sustainable Data Centers team at Google. Technical for, I guess they call it carbon intelligent computing at Google. And the team that she's working with looks at basically adapting the compute in data centers so that you run more and harder in locations where there is renewable energy available. And so this is a problem that in our group we've really enjoyed working on for the last 10 years, and something that we're really trying to push. And when you think of this, you think, well, this is an obvious place where AI/ML tools can be really helpful because they can predict the availability of renewable energy, the availability of workloads, and then with those predictions, you can do resource allocation and scheduling to adapt one and match your capacity to the workload and sort of manage these things in a really smart way. And in Google, there's been a lot of work on these AI ML predictions of renewable availability, workload availability, et cetera. And so DeepMind has a couple of really prominent contributions in that area. And so you have, a team at Google working on the compute allocation, a team at Google working on the, prediction, and yet you don't see the ML AI tools used in practice for exactly the reason I described. You can't afford to fail at scale. If your predictions are off for an unexpected reason, and that leads to a really poor system configuration or capacity management decision, then you're in big trouble and you just can't take that risk. And so you tend to use more kind of traditional optimization, robust optimization-based tools in practice when you're doing this sort of thing. And here's a simulation from our lab now that kind of demonstrates why this happens, what the risk is here. So this is a simulation of real workloads for capacity provisioning with of a data center with on-site solar and storage, and the y-axis is the average cost. The x-axis is distribution shift, and what I mean by that is you're training an ML model, a deep neural net here to predict, and if you're at distribution shift 0, then the test case, the real world, matches the data that you trained on. Here, there's a bias in what you're testing on versus what you trained on, either positive or negative. So that's the distribution shift. And if you use a robust optimization, sort of non-ML based tool, this distribution shift doesn't matter to you, so you just have the same performance everywhere. If you use your ML-based tool, your deep net, then if you're right, if the training matches the testing, you're going to be really good, and you're going to get a nice, significant improvement in cost. But if you're off, if there's distribution shift, you can have a big risk. And so there's a big win if the training is good. There's a big risk if the distribution shifts, and this risk is just not something you can take on in practice. And so what you want is something that looks more like this, where you get most of the gain from the AI tool if things are right, but you curb your risk, you bound your risk in situations where there's distribution shift from training to the deployment. And so that's the goal. And said in a sentence, the goal is, can the guarantees required by safety critical applications be enforced by the ML tools, by the AI ML tools? And so, in cartoon form, this is the way I think of it. You have, these black box AI tools that can get you really good performance, but suffer on robustness and safety. You've got your more traditional model-based control, online optimization, online algorithms-based tools that get you robustness, but suffer a little bit. They get fine performance, but they suffer a bit compared to the AI black box tools. And, right now it appears that there's this, sharp trade-off between them. And what we want to do in the, in the research agenda for this kind of direction is to say, can we get something that gets the best of both? Can we get the benefits of both? And, maybe we could even be all the way out here, but, can we somehow combine and get the best of these? And in the parlance of more the applied probability or control language, you can think of this as model-free tools can't give you the guarantees for robustness and safety off the shelf. You need sort of model-based tools to be able to get these robustness and safety guarantees. And so the middle is some sort of hybrid model-free, model-based approach. And there's a lot of results in that domain that have emerged in recent years. Including sort of model-based RL, Lyapunov-based policy learning, model-free policy search, safe RL, where you sort of embed RL with some of these models. Lots of different ways to kind of try to embed the sort of stochastic model-based guarantees with the model-free learning that we see in these modern AI tools. And then, so those are, the top four I kind of highlight because those are the sort of more stochastic type approaches. These bottom ones are a little bit less rigorous in the stochastic sense, but, you can imagine doing adversarial testing of the model-free tool to try to show that it can't break, or do verification of the model-free tool in some sense. And there's a lot of interesting work in both adversarial testing and system verification for black box AI as well, to try to get that kind of middle ground where you get some guarantees without giving up much of the performance of the black box tool. And so that's kind of the the space that we've been thinking a lot about. And this is also one of the driving questions in the emerging field of learning and control. And so if you're interested in this stuff, check out the main conference for that area right now is L4DC, Learning for Dynamics and Control. And there's a number of workshops at IPAM and other mathematical institutes over the last few years where you can see some nice slides. And we at Caltech organized a virtual seminar series on this topic during the COVID time, where there's a nice archive of talks if you're interested in learning about this style of work and in this emerging field. I think it's a pretty exciting field. And I always like to poke fun a little bit at this emerging field. This really is in the emerging phase right now, where there's a lot of work that kind of strives to do this in some specific context. So you can sort of say, like, I want to make RL work for voltage control. And so to do that, I need to find a way of making the RL stability constrained. And so you take kind of your guarantee that you want for your application and the AI tool that you want to apply, and you combine them and you get a great paper for this field. So I think it's a really fun field to sort of go after. And there's a lot of low-hanging fruit still at this point in terms of trying to figure out how to adapt these AI tools to specific applications to get the guarantees that you need there. But it sort of looks at times like a little Mad Libs for these titles, and just to make sure I'm poking fun at myself here and our group a little bit too. But today I think the field is moving to the place where we're starting to understand more general approaches for how to do this, rather than specific approaches tuned to specific applications. And the Lyapunov-based tools for reinforcement learning and policy learning are one great example of that. And there's many other such tools that are emerging as ways of getting these general results beyond taking advantage of one specific application. But today I'm going to talk about one that we've been working a lot on. Not the only one by any means, but one that we're excited about. And this one I sort of refer to as a K-experts approach for getting the best of both worlds. And so if I come back to my cartoon, this is the way I want you to think about it. So I want you to think about, we're going to try to come up with algorithms where we treat the black box AI as an untrusted expert. So it's somebody giving us an advice about what action to take right now, but we don't really know how much faith to put in them. And we're going to try to take that input and combine it with what we could get from our trusted expert, our kind of control online algorithms based prediction. And that's also going to tell us something to do. So we have, an instruction of just do this and you'll be great from the black box AI. And we have an instruction of just do this and you'll be great from the traditional algorithm. And we want to take those two suggestions from our two experts, combine them, and then decide what we're going to do. And so that's the task here. And so we're taking untrusted experts, combining them with trusted experts, and somehow ideally getting out a choice where we can certify that we'll have a robustness and safety guarantee, but at the same time, we can certify that we're going to be nearly as good as the untrusted expert when the untrusted expert is good. So that's the goal in sort of a high-level form of this style of analysis. And the key thing here is we're not going to pay attention to how the untrusted expert works or how the trusted expert works. We're just going to take their suggested decision as the input to our algorithm. So we're not going to mess with that. We're not going to make a decision based on whether we're doing RL or deep learning or whatever it is on the untrusted side. We're not going to make a decision based on what the algorithm details on the trusted side are. We're just making decisions, treating those experts as black boxes. And then try to get the best of both worlds by combining those decisions. And so to make that a little bit more concrete, because right now I haven't said what performance means, I haven't said what robustness means, and you could imagine lots of different stochastic or adversarial ways of thinking about that. And there's lots of papers that take different views on how to think about what those are, what those measures are on either side. For this talk, we're going to do an adversarial viewpoint. And so we're going to take two measures here, and we're going to look at a bi-competitive guarantee with respect to these measures. And this, in the literature, these are referred to as consistency and robustness. And so consistency is the measure that says we're going to do as well as the black box AI when it does well. And so mathematically, that means that the cost of our algorithm, the one that's combining them, is going to be not much worse, delta is some small constant, not much worse than the cost of the untrusted algorithm. So this isn't binding when the untrusted algorithm does bad, in the case that it thinks the stop sign is the speed limit sign. But if it's doing really well, this is a very binding guarantee. And so when it's doing well, we need to do is basically as good as it. And then at the same time, we want to ensure robustness. And here again, we're going to take an adversarial guarantee, and we're just going to say that there's some competitive ratio, some approximation ratio where the algorithm is a constant factor worse than the optimal. And we want that constant factor, that competitive ratio, to be nearly as good as the competitive ratio of the trusted expert that ignored the AI entirely. And so we want these to be close. They won't be able to be as close as the 1 plus delta. And you can think of this like competitive ratio as, if you want to anticipate the results, as being a function of delta. So how close you are in consistency, how close you are to the black box AI when it does well, means that you're going to give up something in robustness. So there's going to be this trade-off curve between consistency and robustness. That's a function of the delta in the results. And so, as I've described it, this is sort of a K-experts framework. The contrast to the classical K-experts or bandits literature in online learning is the fact that we have trusted experts with guarantees that we want to maintain. So, it's not just that we're pulling two arms for our bandits, or we have two experts and we don't know anything about them. We know that one of those experts has a guarantee where if we followed it, we'd always adversarially be good. We'd satisfy this competitive ratio of gamma trusted. And we want to maintain that as much as we can while still being as good as the other arm when the other arm is good. So it's this kind of trusted guarantee, which is what makes this different than sort of the traditional K-experts literature. And just to drive home this in the context of one very common algorithm. So if we think of control, model predictive control is the algorithm that just treats the predictions it gets as correct and follows them in a certainty equivalent way. And so that kind of algorithm is going to do really good for consistency. If the predictions that the black box is giving you are good, it's going to be really good because it's following them very well. It's optimizing based on trusting those predictions. But if those predictions are bad, then it's going to be terrible And so it's going to have terrible robustness. And so that's going to be like very good for goal 1, but very bad for goal 2. And we can see that here. So this is a trajectory planning problem where you have a drone that's following a particular trajectory. And so we've modeled the dynamics of that. And if the predictions are good, then MPC is going to do very well. But if the predictions are very noisy, then MPC has a really hard time because that it's trusting them and the predictions are guiding it wrong. And so it's this figure on the right that we want to avoid. We want to be able to still maintain the figure on the left, but we want this figure on the right to be robust to even bad predictions in this framework. That's the goal. Okay, so this is a good point for me to pause and say, is this trade-off between consistency and robustness clear? Do you have questions on it?
So I know you want to keep the discussion at the intuitive level probably at this stage, but are the cost in your goal 1 and the cost in your goal 2 defined or calculated differently?
No, same cost, and I'll make it really concrete in particular applications. But you can think about this, in whatever application you're thinking of. This is just the cost you care about in that application, and it's the same cost here. It's just you want it to be good compared to that, and good compared to that. So you want a competitive bound with respect to both the AI and with respect to the offline optimal.
I see, but the cost, I guess, where does the adversarial type of guarantee comes in here? I thought like there's a natural adversarial interpretation for the second robustness cost, but what about the first one here?
So we're not making any sort of assumptions on the workload or on the predictions, quality of the predictions here. And so, the algorithm, regardless of the quality of the predictions, should be nearly as good, and regardless of what the workload that's coming in is. So the workload could be constructed adversarially to try to make you perform worse than the untrusted algorithm. Yeah.
Okay.
Yeah, so it's sort of, these are both competitive bounds. It's just the benchmark that you're comparing against is in one case the offline optimal, and in one case the performance of the AI, if you just followed it without, completely blindly. Any other questions now? Okay, then I'll make it concrete. So this framework is called, online decision making with untrusted advice. And the idea here is that you really make no assumptions about how good that untrusted advice is. And it was introduced in the context of online caching just a few years ago at this point. But since then, during COVID time, there's been a huge progression of work in online caching, but also lots of other applications. And across these, some of these are adversarial, some of these are more stochastic in the guarantees that they're looking at, like the work here and the work here are more stochastic. And I know there's some ongoing work applying this tool in the problems like scheduling that are sort of core to this community as well. And so you can really apply this framework as I've described it in a wide variety of settings and get interesting results. And the ones here are the ones that in our group we've been working on. And so we've, if you have questions about any of those, I'd be happy to talk about them after the talk. But for today, my goal is really to sort of give you an idea of how to think about algorithm design in this context, rather than to go into the details of any particular application. And so I'm going to try to give you sort of a structural set of questions around what are the fundamental limits on different types of algorithms in this sort of space. And we're going to do that by looking at 3 applications. And so the convex body chasing, online optimization, and then I'll just say a tiny little bit about LQR control in one context to introduce one idea about the algorithm design. Okay, so jumping in then, I'll start with convex body chasing. So now at the end of this, it should be really concrete what we're thinking about in terms of robustness and consistency. So here, convex body chasing is, you can think of this as a safety problem where you're choosing some action for your system. And at each given time, there's a set of safe actions that you can choose from. And so you have to be choosing an action in that safety set in each round. And you don't want to change your action dramatically at any given point of time. So if you think of, a drone or a autonomous vehicle, you don't want to be wildly changing the direction. And so changing your system configuration at each time. You want to have smooth steps from one state to the next, but you have to be in this safety region. And so this is going to happen over and over again. And the cost you pay is your distance between your actions. And each time you're moving into the body. And so what I've just shown here is kind of a situation where you're kind of moving to some sort of center of the body in each time. And your cost overall is the total of your movement costs, so some distance norm here. And the challenge here is that you don't know what the future bodies are going to look like or where they're going to be. And so you don't know where in the current body to move, because you could be strategic and try to guess where the next one is going to be. But then if you're wrong, you end up far away from the future bodies in the set. And so it's hard to sort of decide where to go without knowing the future. So that's the algorithmic problem. And this is a problem with a really long history, 30-40 year history at this point, and a lot of very interesting results over that time. These days, it's becoming particularly interesting in the context of control, which is the language I just described it, for safety and stability. And so we have some papers that, if you want to learn about this, you can look at, where the idea is, think of trying to control a system where you don't know the dynamics of the system. So you don't know the stochastic evolution going forward of the system, and that could be changing over time. And so you need to learn the system as you're controlling the system. And the way you then use convex body chasing is in a nested form, where at the beginning you have some set of possible models that the system could be following. And then with each step and observation of the system, you learn a little bit about the system. And so you update that set of possible models that are consistent with the system. And in that way, it shrinks over time, the bodies that you're chasing, because every time you learn a little bit about the system, the set of consistent models that could explain the behavior you've observed shrinks. And so you're basically, in these papers, the algorithm design is you play a robust controller at any given time step. And whenever it makes a mistake, you learn about the models that could explain the system. That set shrinks. You then choose a new approximate model that's in that nested body, use the robust controller until it makes a mistake, and so on. And you can prove, using this convex body chasing literature that I'll explain in a little bit, that you'll make a finite number of mistakes in any long horizon in an adversarial sense as you learn the model while controlling it with this style of algorithm. And so convex body chasing has been really crucial to getting these safe controllers in contexts where you don't know the underlying dynamics of the system. And so that's one application in that, but there's many others in the sort of control literature for this convex body chasing work. And motivated partly by that, but also by other applications of convex body chasing in other areas. There's been a lot of recent work in this domain with, I'd say, some of the state-of-the-art results being due to Mark Selke and Sebastian Bubeck, where basically at this point, the best known algorithm from the traditional adversarial competitive ratio sense is to move to the Steiner point of each body at each round. And the Steiner point is just a notion of the center of the body. And if you do that, you get a competitive ratio that is nearly square root d, where d is the dimension of the problem, the dimension of the space that you're in. And you have this log t here, which is kind of annoying because the lower bound of any algorithm is root d. And so you're kind of nearly getting there. But I guess without the t, you still have a square root gap between the d and the root d with the Steiner point algorithm. And we don't know at this point which of those is tight, actually. But that's the best known algorithm so far. And you can sort of think immediately to yourself, this is a really conservative algorithm, because at every given point, it's just moving to some notion of the center of the body. And if we go back to the example I drew before, if we knew what was coming, if our black box AI was really good at predicting what was coming, then we could have just moved to this intersection of all those bodies and never moved again and done way better. And so if we have predictions from our black box, from our untrusted expert that are good, they're really valuable in this context. But of course, if those predictions are bad, they can really screw us over, right? So we can end up making wildly large moves unnecessarily if the predictions are off. And so, that's the point here, right? If we're just ignoring predictions, we can be conservative, but we're going to give up a lot compared to if the predictions were good. But we need to make sure we have some way of hedging so that we don't get thrown off by bad predictions. And so when we think of algorithm design here with that goal in mind, the first starting point is, well, we have two pieces of advice from two different algorithms. Which one are we going to follow? How do we decide when to follow the trusted advice versus when to follow the untrusted advice? Naturally, there's kind of this idea of, well, maybe we follow the black box AI until it does bad in some sense and then switch away from it. But then what if it just makes one mistake and it's good after that? So how do you decide when to switch back to it and all that sort of thing? David, question, jump in.
Hey, Adam. So,
hey.
So high level question, so thinking to the connection with experts that you talked about before, what if you just threw in an expert that just played the Minimax strategy and then did experts with respect to the Minimax strategy and the people that maybe or maybe not are good? Would that, what would that mean here?
I'm starting to think that as well. So the experts compared to the Minimax strategy.
Well, I'm just thinking, because you said a key distinction with experts is that here, maybe none of them are good, but what if you just threw in a bogus expert that just mimicked them in the adversarial setting?
Yeah, so I think ideas like that are good. And in some applications, so there's one application that I know of so far where people have been able to apply something along those lines, where you end up with sort of a probabilistic algorithm that's mixing choices and you can pull it off. It doesn't seem like, at least so far, we've been able to follow that approach in general. You'll see in just a second the sort of, I'd say, vanilla approach that people work, which is it has that flavor, but it's more of a doubling style algorithm to get an approximation of that. But yeah, you'll get a sense of like the two ones but I think this is a new enough area that I can't say that won't work by any means. I think people are still exploring what frameworks to use here. So let me jump to that with that as motivation. So one way of kind of like understanding how to mix between these, and in some sense trying to be smart about mixing the two, so maybe defining kind of a minimax strategy like David was talking about, is what is very natural if you're familiar with the online algorithms world, where you follow sort of a doubling algorithm. And the way this doubling switching algorithm would work is, initially we follow the untrusted advice because if it's really good, we should start there. Otherwise, we're going to all immediately give up something compared to it and not be able to be consistent. And so we follow the untrusted advice and we're going to follow it until we reach some threshold R of distance traveled. And if the untrusted algorithm is really good, that's going to take a while to get there. If it's really bad, we'll get there really quickly. And so this already has a nice kind of intrinsic follow it for a short amount of time if it's bad and a long amount of time if it's good. And then we follow the trusted advice until that same threshold of cost R is achieved. And again, if the trusted advice is way worse than the untrusted advice, this will be a shorter period of time than step one. If it's way better, then this will be a longer period of time than step one. And so we're getting kind of a natural balancing in the way we'd want from doing this. And then we double, because we can't just make this one decision forever. So then we double R and we do the same thing over again. And then we double R and do the same thing over again. Okay, so this is a very natural way of looking at this. And I think this simple algorithm already drives home a nice point, which is I don't care whether you're using DeepRL or what algorithm or what sort of policy learning you're doing for the untrusted advice. And I don't care what the algorithm is for the trusted advice. I'm not even looking into that. I analyze this algorithm completely independent of what's happening in either of the experts, and I can still give you a guarantee. And then if we care about, really biasing towards consistency or really biasing towards robustness, then we just choose not R in both places, but 2R in one place and R in the other, or some ratio between these that helps us bias towards either consistency or robustness. And so we can optimize in that way as well. And so this style of algorithm with not with a straight RR, but with a carefully chosen bias between them, actually works in the nested convex body chasing case, which is the case that's useful for like these online control, safe control problems. And so here, this gives a nice example of kind of a best case result one could hope for in this framework. So you get for nested body chasing, switching algorithm is 1 plus delta consistent. So we're matching up to an arbitrary small constant, the black box AI. But we pay in our robustness guarantee 1 over delta, depending on how close we are in consistency. But notice that the D here matches the best known competitive ratio for any algorithm in body chasing. And so we're getting, we're not giving up anything in terms of the robustness factor. We're just giving up a constant 1 over delta in the robustness factor compared to what we could if we didn't have any learning involved. David, go for it.
So this one's, even more high level. Like on the trusted side, do you need to know how much you trust them in the beginning, or does it tune to this, or is this?
So the way the algorithm works, that this particular algorithm works, is you set the ratio between this R as a function of the guarantee that you've proven for the trusted algorithm. And
like,
so
is there a sense in which does the algorithm know in advance how much you trust them, or does it like learn on the fly in some sense?
Oh yeah, that's a great question. So in all the results that I'm talking about, we know ahead. So we know that guarantee ahead of time for the trusted algorithm. And we could even use that like guarantee.
Is it like a number, like I trust them 80%, or is it just binary, like I trust?
No, it's that competitive ratio. It's, the competitive ratio of the trusted algorithm is gamma trusted.
I see.
So the bound. It's not a like probabilistic trust. It's that if I ran this algorithm, I would have this guarantee on my performance. Now, can I keep something close to that guarantee while still using the AI tool to help me make decisions better?
Okay.
And so you can think of this as like a direct analog of that, like executive coming in and saying, I have a system right now that has this guarantee. I don't want to give up this guarantee, but I want to, test out this black box AI that my team's telling me is better. How can I test that out while still maintaining the guarantee I have in my current system? So your current system is your trusted advice, and your, experimental system is your untrusted advice, and you want to mix
Got
it. Yash, did you have a question? You turned on for a second.
I was just asking, this O of D you said is the best you can get for convex body chasing. Is that also the best you can get for nested convex?
Great point. No, you can do slightly better. I should have said that. Yeah, so this is the best for general body chasing, but not the best for nested. That's a good point. We should be able to get that as well. We just haven't pushed on that.
Got it. Thanks.
Great question. Fernando, go for it.
Hi. Yeah, I just didn't catch what nested was.
Nested is all the bodies. The next body is going to be within the current body.
Okay, but so it doesn't move. It just converges.
It just shrinks. Yeah.
Okay.
Yeah. So think of the motivation for this as you have a consistent set of models for your nonlinear control problem, but every time you learn a little bit more, that consistent set shrinks because you've ruled out some of the models as not consistent with what you saw.
Okay, thanks.
Okay, and so thanks for the questions. This is great. And so, but I want to emphasize here, this is a really powerful style of result because it says, if you're running some deep RL for convex body chasing, we're going to give up a delta factor of that. But now all of a sudden you get a adversarial worst case, robustness guarantee for your deep RL for free, just by running this simple wrapper on top of the suggestions it's giving you. So that's the power of this kind of result. But as we said, this is limited, and because we're requiring just the nested here. And this is where we get to our first fundamental limit, and this is a limit on switching algorithms. So this says that if we use an algorithm of some sort of form like above, where we're only choosing one or the other of the advice to follow, we can't hope for a result as good as what I just showed you for the nested case in the general case. And in particular, you have to give up at least a factor of 3 compared to the the untrusted expert if you want any sort of robustness guarantee, even a bad one. If you want any sort of robustness guarantee, constant competitive ratio, then you can't be better than 3 consistent, which is not great in that scenario. And so we have to go to more complex algorithms. And so here's what we have so far as a more complex algorithm. And so just to give you an idea of how it works now, basically what you want to do to be more complex is, instead of always choosing here, the blue is the trusted expert and the green is the untrusted expert. Instead of always choosing one of them, you want to choose some combination of them, and you want to take advantage of the fact that these are convex bodies. So you know that the everything on the line segment between them is within the convex body. And so what you want to do is adaptively decide where to balance between them. And so, concretely, you want, if the the trusted expert is much better than the untrusted expert, then you just follow the trusted expert and you have both, you have consistency and robustness for free. But if the untrusted expert has costs that you've seen so far up to time t better, then you need to hedge. And so here you take a greedy step from the untrusted expert towards the greedy expert, or towards the trusted expert. And the length of that step varies adaptively depending on the experienced cost so far of the 2 algorithms. And it's a bit of a complicated formula, so I'm not writing it, but think of it as just adapting, where if the untrusted, the cost is much better, you're very close to it. If the trusted cost is much better, or if the trusted cost is not much worse, you're getting closer and closer to it in this bounds. And so you adaptively move on that line segment. And then you end up, the results that you prove here are in a domain called bi-competitive line chasing, because you don't care actually anything other than this line in the body. So you're just chasing now lines, and you're trying to be competitive with either input of that line, which is a different line algorithms problem. Okay, and so again, the key thing here is I don't care about how these advice are generated. I'm just hedging between them based on the performance they've experienced on this instance so far. Varun, go for it.
Quick question. So is there an assumption that the untrusted algorithm, like what if it adapts its actions based on your past actions? I guess that's the assumption, that it doesn't do that. Because then we get into this policy regret kind of thing.
Yeah, that's a good point. So yeah, so the untrusted expert is not adapting based on it can learn from history within itself, but it's not adapting based on the trusted algorithm or in that.
Or your own. Okay, thanks.
Yeah, that's right. That's a good point for our, you're thinking ahead in terms of how you would prove this. Okay, and so with this adaptive algorithm, what we get is a result that looks like this. And notice it's still nice. It's still giving us competitive bounds with a robustness bound on top of a black box AI, but it's slightly worse than the nested result in 2 ways, because we now have a root 2 here instead of a 1. So we've sacrificed something in terms of consistency compared to the black box AI. I don't know if that's a fundamental limit at this point. I think there's a fundamental limit here bigger than 1, but I don't know if it's root 2. And then the other thing that is worse is we now have a dependence of delta squared instead of delta. And again, we don't know if that's fundamental or if that's a function of our algorithm here. And so I think there's, this is a nice result, but it's one that opens questions, doesn't close the door by any means in terms of that, what we can hope to accomplish here. Okay, but now, so that's one example on the algorithmic side here. There's a lot you can do with switching, and in a lot of the sort of areas, the algorithmic problems that I talked about so far, all the results are just for switching algorithms. There's not results for other types of algorithms yet. And so in a lot of this space, I think there's room to improve by going to non-switching algorithms. But the next algorithmic question I want to talk about is memory. So the adaptation here uses full memory of the costs of both the trusted and the untrusted advice. And a nice question is that complexity necessary here? Do we need to do something like that in algorithms that balance robustness and consistency, or is that just our algorithm that was using that. And so, yeah, the question is memory needed to benefit from untrusted advice? And so to look at that, we'll go to the online optimization example. And so here, there's actually a nice reduction between these problems, but just to explain it in the way that I think is more intuitive for this, it's a very similar problem, except now instead of getting a body on each round, you're getting a cost function. And you care again about your movement cost, your switching cost, but you also care about your cost on the cost function that's presented to you. And so your cost is the sum of those two things. And again, you repeat each round, you get a new cost function, you pay your cost on that cost function and your movement cost, and so on. And so your total cost then is the sum of your hitting costs and your movement costs. And again, the challenge is that you don't know the future cost functions. And so without knowing the future cost functions, you have to be conservative in where you move. And if you had good predictions, you could be more aggressive and do better. And so, just like in body chasing, this is this is an area with a huge history, decades of history. And in the last couple of decades, there's been a lot of focus on this area from our group and many others because of applications in data centers and video streaming and EV charging and all these sorts of things. And I highlight these four because, here the algorithms in all cases have made it into industry practice. And so you can point to data centers that are using this stuff. And you can point to video streaming protocols that are using, online optimization based policies and all these sorts of things. And so if you watch NBA, then some of the camera tracking algorithms there are using online optimization based algorithms. And so motivated by all these applications, there's been a lot of progress on the algorithms in recent years. And I'd say state of the art at this point are these kind of results. So this is in the alpha polyhedral case. So the cost functions have a steepness of alpha around the minimizer. And when you have alpha polyhedral cost functions in the convex case, you get a root 1 over alpha competitive ratio, and this is tight up to constant factors. In the non-convex case, there's a, actually best known algorithm is just greedily moving to the minimizer because you have to be really conservative, and that gets you a 1 over alpha sort of rate on your competitive ratio. And so, but again, like the non-convex case really makes it clear you have to be conservative in these things. You have to be moving to pretty close to the minimizer. And that means that if you had predictions, you could potentially do much better. And coming back to our example from before, if you had predictions, you could move near the minimizer the first time and then not move anymore, because while you're not at the minimizer, you're close in terms of cost, and it's not worth the movement cost to get to near the minimizer. And so if you had good predictions, you could do much better. But if you had bad predictions, they could really mess you up and get you to incur movement costs when they weren't necessary. Okay, and so in this case, actually, it's interesting because we'll look at the non-convex problem, and the non-convex problem is interesting because the best thing you can do in that context is switching algorithms. And you can sort of think about, right, if there's non-convexity, you can't hedge between advice because you might, have a big bump there that makes you pay a huge cost. So you have to really be doing switching algorithms. And so an adaptive switching algorithm, sort of along the lines of the one I showed you, a little bit more complex, gets a result that looks like the following, which is, again, oh, and I should be giving the students that credit. So this is work by Nico and Don and Deb with me. So Deb and Don are at Georgia Tech, and Nico is one of my students at Caltech. And here, this result is, nearly as good as the first one I showed you. We're getting this 1 plus delta factor here, but we get a way worse robustness trade-off. So this is now exponential in the delta in terms of what you pay and your robustness factor as you get closer and closer to the consistency. So this is in some sense a harder domain to be robust and consistent in than the body chasing problem was. But it's still, a black box AI. You can take your deep RL and you can get a provable adversarial bound on its performance by wrapping it in this switching algorithm. I guess emphasizing what I said, in the non-convex case, switching algorithms are provably the best you can do. But in the convex case, you can do more sophisticated algorithms that hedge, like I showed you in the body chasing world. And then this exponential trade-off is a bit disappointing at first, but you can come up with a lower bound that shows that actually this sort of exponential trade-off is necessary for any online algorithm in the case of non-convex costs. So you can't hope to improve by this by more than a constant factor. But I'll now show you sort of the good news and the bad news of deploying these algorithms. So one thing I want to emphasize that before I show you the results is this delta. So I haven't spent much time talking about it, but this is a trade-off parameter where if you want to be nearly as good as the black box AI, you set it really small and you pay your price in terms of robustness. But of course, if you know something about the trust, as David was asking about, in your untrusted advice, then you could set this more aggressively or less aggressively, depending on how much you're worried about that untrusted advice. And so there's really something here that needs to be tuned depending on what you expect to see in the performance of the algorithm. And so to look at the performance of these algorithms in a real context, we'll come back to that sustainable data center problem that I like so much that I mentioned at the beginning. And so here we'll use this algorithm, and we'll have a deep learning based predictor for our black box AI. And this was the model I showed you before, where we had the deep learning and the offline algorithm, or sorry, the online algorithm that doesn't use predictions. And I showed you your goal before, and actually that goal line was our algorithm performance. So in the real situation here, you apply that switching algorithm on top of the black box AI, and the performance you get looks like this. So you get, in terms of the case where you have no distribution shift, you're getting nearly all of the gain that the black box AI is giving you. But in the situation where you have massive distribution shift, you're getting a really good, even better than we'd hope, better than the theory would suggest, robustness guarantee on the performance of your algorithm. And so you're able to kind of get a best of both worlds just by adding this simple switching wrapper on top of your black box AI and your trusted algorithm. So this is really exciting when we saw this, actually. But this is a little bit of a, I'm cherry picking here, because depending on on how you choose the delta, you get a wide range of choices here. So if you choose it more aggressively than you should, then you still have a big loss here. If you choose it less aggressively than you should, you get it down here. Varun, good time for a question.
So, I mean, one thing I've wondered is so suppose there are periods where the trusted algorithm is good, periods where or the other way, sorry. Yeah. Is the switching algorithm doesn't seem to sort of adapt to those things, right? Because you're doubling everything. So how in practice, do you think you'll do it every day, somehow restart the algorithm, or?
Yeah. So the doubling, as you know, is very powerful in the sort of proof. In practice, you give up something because of that. You are being adaptive still in that situation. And in terms of, a ratio of costs, the doubling comes because at that point you've experienced that much cost. So anything you give up there is still now a small fraction. And so you can, of course, in practice, adapt the doubling, and maybe that makes the, competitive bound look a little worse, but maybe in practice, it makes you more responsive to, the changes in the environment. So I think all of that stuff can be, done maybe more with a experimental study to set those parameters. But as this, this is one of the other parameters that you need to set. And as you can see, there is work to be done in tuning those parameters right now, as I've stated it, to get you to a situation where you're getting the most out of the algorithm in that scenario. And so this is a place where I think theory can still convey new stuff. And actually, that's my next point. With this parameter, there's a delta that you're trying to set. And what you'd want to do is learn how to set that parameter online. You could imagine doing the same thing for the doubling parameter, like you asked about, Varun. And in the case of learning the delta online, we don't have a result yet in the case of online optimization, but this is where I'll very briefly switch gears to the LQR setting. So if we imagine a control setting where we have linear dynamics here, and we have quadratic costs like this, now I can actually prove something about how to adapt for that delta robustness versus consistency result. Bo, just 1 second and I'll get to you. And so here, what you can get in the adaptive style of results is something that looks like this, where no longer do you have a guarantee that's trading off consistency and robustness in terms of delta, but now you have a guarantee that's a function of this is the overall prediction error in the sample. And you get a prediction. This basically, in math, this corresponds to selecting an algorithm that is the lower envelope, has the performance that's the lower envelope of any delta. And so you get something that looks like the lower envelope of all the deltas instead of choosing a specific delta. And the way we can get that is with, actually fairly standard online learning tools, which, follow the regularized leader approach to that adaptation. But we don't know yet how to do that in the nested body chasing or the online optimization world. But, the control world is a little simpler to do these proofs. And so we were able to get a result there. Bo, go for it.
Hi, Adam. So in the previous slide, it seems that when you choose the delta property, you can even achieve a better performance than both untrusted and the trusted advice in some cases. So
no, so this is just overline. It's just that line's a little thicker. I tried to trace it to make it look. So you're matching. Oh, but out here, yeah, you're getting.
In some cases, yeah.
Yeah, that's true. In this elbow, you do get better.
So any intuition behind that? That seems to be pretty interesting. Right? You can do better than both. I'm not sure if I missed anything.
This is sort of a weird place where they're both a little off, right? So it's not that non-intuitive actually, because here, the black box is optimized for this point, so it's performing poorly because it's off on its predictions. This is optimized. The black line was optimized for this point, really terrible predictions and not letting them hurt you. And so neither is optimized for this point.
I see. Okay, yeah. Thank you.
So it's not that weird that it shows up, and it's just this little region there. I wouldn't put too much importance in that. David, yeah.
Have you tried combining it with this bandit over bandits framework where you kind of run the algorithms for different deltas and kind of have a meta algorithm kind of deciding between the algorithms?
We have not. This was kind of a layer on, and our goal was to get something provable. We have not done a lot of exploration in this for this adaptation to delta at all yet. So this was like, where do we think we can prove something? This framework, had required the right properties where we could get a theorem, basically. Yeah, so if you have ideas, we should go. We should think about it. Okay, and so on this, just to come back to the tracking problem, and then I'll wrap up. In the tracking problem here, this was the figures I showed you before. If I show you now that algorithm with the follow the leader adaptation and really, really noisy predictions, you can see the blue line here. It is our algorithm, and it messes up a little bit a few times, but compared to what a certainty equivalent control would do, you're just orders of magnitudes better. And I should say this, from the control perspective, the algorithm that you ending up with, where you take follow the leader and you combine it with this like offline and MPC with a sort of offline control algorithm, it's not actually that weird a control algorithm. It actually starts to look pretty close to some of the robust control algorithms that exist in the literature, but the guarantees and the proofs that you can do for them end up very different. And so it's giving you sort of a different style of guarantee for algorithms that are in the family of things that do exist in the literature in the LQR sense. Okay, so I did want to show one more result here because I wanted to say something about memory. That was why we went into this application. And so, when we're adapting, when we're using follow the leader to set the delta, and when we're doing this adaptive online switching, we're again depending a lot on memory to get these results, and that's necessary. So in this context, again, we can prove a limit that says that if you don't use memory, you can't benefit from untrusted advice. And so what we mean by that is in math here, it says if we want any sort of competitive ratio for the algorithm, then the best consistency guarantee we can get if we don't use memory in the algorithm is 1 over root alpha. And remember, that's something we could get even without using any predictions in the convex case. And so in the convex case, we can't get any competitive ratio for consistency better than we could get in a pure adversarial way without using any predictions if we don't use memory for the decisions. And so we have to be using some memory. Now we can't clarify how much you need, what's the information, in the information theoretic sense, how much do you care about the memory? Can you get away with little bits versus a lot? I don't know that yet, but we do know that you need some amount of memory to make these, to get results that are that benefit from these black box AI. Okay. And now, just as a final little nice result here, this requires being in the two-dimensional case. In the one-dimensional case, actually, you can get around that lower bound, and so in that case, you can, in convex cost functions, one dimension, do an adaptive version of that kind of best state-of-the-art algorithm, online balanced descent, and get a nearly optimal kind of robustness versus consistency trade-off, where the only thing that's a little suboptimal here is the 1 over delta squared versus 1 over delta. And we don't know yet whether that's a weakness of our analysis or our algorithm, or whether that's a lower bound. But I think, this, I'll say this is, seems like a smaller case than the rest because of the one dimension, but actually the one dimension case has gotten a lot of attention over the literature because of a couple different applications where that's one dimension is all you need. And so this is a meaningful problem to try to improve on if you can get around this 1 over delta squared lower bound. Okay, and that's where I'll end for today. So I just want to kind of wrap up and say, my goal here wasn't really to get across any specific result of from our papers. It was to sort of expose you to this idea of a K-experts approach for combining, black box tools with more trusted experts from the model-based, control online algorithms world. And so, this was the picture I hope you take home, the consistency versus robustness by combining these two experts. And the results I showed you were trying to give you a flavor for how algorithms are designed, like whether you can get away with switching, whether you need memory, that sort of thing. And we're starting to understand sort of the limits of each style of algorithm at this point, at least in a few applications. But I think there's a lot more open questions that are left to look at because this is a new emerging area. So looking at adapting to the quality of untrusted experts, we only have that very small initial result. I think that's a really important problem for this field. Follow the leader is one approach, but David already suggested another one that could be better. Another one that I think is really interesting here is suppose the untrusted experts come with uncertainty quantification of some form. So they tell you not just a point prediction of do this action, but they give you some quantification of confidence interval or trust confidence in that action. That, of course, would be really useful. How do you make use of that when combining it with trusted experts? And then everything I talked about was one untrusted expert and one trusted expert. But suppose you have multiple untrusted experts, multiple models that are giving you suggestions of what to do, and you have multiple online algorithms. Maybe one gives you a safety guarantee, one gives you a competitive ratio, one guarantees stability for you. How do you combine them with untrusted experts to get all the guarantees and still take advantage of the black box AI? And can you do that without kind of delving into the details of the algorithms? I think these are all really interesting questions. And then, I think a couple of the questions we're hinting at, what if things are changing online, either the untrusted expert changing online, or maybe the trusted expert, you don't know the model to be able to use it right away, but you gradually learn the model as you go along, and then you can get your trusted guarantee. How do you take advantage of, how do you adapt this sort of framework to handle that kind of uncertainty? So I think there's a lot of interesting questions in this domain, and my goal here was to, intrigue you enough to dig into these papers and start to think about how you can ask these questions with your own research. And I think, it's a really rich area. So I'll leave you with that, and thank you very much for your time. Thanks, David. So any questions? I know I'm a little long, but we can take, I guess, yeah, but I'm happy to take a couple questions before signing off. Fernando. I think that's a question, not a clap.
Yes, yeah, it's a question, sorry. One distinction I didn't catch was between basically actions and state in this discussion. It seems like your plot suggested you're controlling directly the state. Is that so? I mean, the convex regions are in the state or in the action?
In the action. So everything that I'm doing is in the actions. So it's the
where's the state? I mean,
actions.
in terms of moving a body or something, the real issue usually is constraints are in the space, not in the action, right?
Yeah, and I think in the control context, this is a really important distinction. And in all of the work that we've been doing in our group, we're actually you can go back and forth between these to some extent, but for getting these adversarial guarantees and for a lot of the learning plus control work that at least we've been doing, it's powerful to think of everything in terms of the actions, because the actions have an immediate impact, whereas the state kind of evolves and has all these dependencies, and so it's harder to kind of do the learning and the adaptation in the state space than it is in the action space, at least the way we're doing it.
Okay, thanks.
David.
So I guess like thinking in analogy, it's just like plain vanilla bandits or something where, right, there's also some arms and maybe you have different priors on the arms. And so, at a high level, how should we think about the analogies of this to, like, if you wanted to do it in a Bayesian framework where maybe in some sense there'd be a naive way to model your trust. It would just be a prior, and then you would just do the control problem in, based on, in a Bayesian sense. How would we think about the connection?
Yeah, I think there's definitely some results that maybe are really low-hanging fruit in terms of viewing, depending on what guarantee you want. So if the guarantee you want is on a more per action basis, then this Bayesian bandit setting could kind of come over very directly, especially if like you're looking at these things in a stochastic guarantee sense on either the optimality or the robustness side. I think our goal is more on, I think, coming from the control space, really motivated by these safety guarantees where you really care about a particular cost, or you care about stability, or you care about a safety region that you need to maintain your place in. And so in those, the sort of typical bandits results aren't enough. Like, it's not enough to think about this as a Bayesian estimation of the arm and some guarantee there, because you really care about a safety critical guarantee that you're trying to enforce. But I think the framework could certainly be beyond that. It's just, the questions we've been asking have been motivated by that.
Cool.
Yeah. Not sure who put their hand up first, but Ming, maybe.
Okay. Hi. I have a clarification question. Maybe I forget that. Is that consistency depend on the instance of the problem? So, for example, so if the realization of the input of the problem is different, then the performance of the underlying machine learning algorithm will be different.
Yeah, so it's adversarial instance based. So on every instance, you want to match the performance of the black box AI up to that delta factor in an adversarial case, in an adversarial way. Okay, so the max over all instances of that ratio.
Yes, from the figure you showed just now, it seems like the consistency, you mainly focus on the case when the underlying algorithm, the performance is good. So you won't get very close to that good performance.
Yeah, and that's because if the underlying algorithm, if the black box AI is bad, then it's really easy to get a consistency guarantee. Basically, it's almost not binding in that case. And so if you think of the proofs, think of like, it's easy to rule out the case where the algorithm behaves bad because your cost is guaranteed to be lower than that. The hard part is to show that you're good relative to it when it performs well.
Okay, good. I see. Thank you.
Yeah, I think you got it.
So I want to ask if, like, conceptually, if you think about what the algorithm is trying to do here in the control context, is it just substantially being able to reduce the possible actions or the action space from like many possible actions to just like 2 actions, one suggested by the expert and the other suggested by the robust algorithm here?
So, I would say a little bit more than that, but yeah, in the control space, like in the LQR, you have convexity, so you're looking kind of at that line between the actions again, like in the body chasing world, and you're trying to select from there. So one benefit is that it does give you a suggested set of actions That's a very low dimensional space. But I'd say that's a help in the analysis, not a benefit beyond that. I think the benefit, that you really focus on is that somehow you can prove that the actions on that, especially if you choose them adaptively, have guarantees that the two suggestions would have had. So like you're able to show that the performance of the adaptive choice between them is good, as nearly as good as the performance of either of the suggestions would have been, without knowing which one's going to be better in the long run, because you don't know the future, right? If you knew the future, you would know which one was better and you would just follow that one the whole time. But since you don't know the future, you don't know which one's better. And you want to mix between them in a way to ensure that you have a good guarantee with respect to either.
And you would allow, I guess, by the analysis framework for the performance guarantee you provided, you would allow the underlying environment to be non-stationary. For example, it actually moves from one parameter region to another.
That's right. That's a benefit of the adversarial, is that I don't care about any of the movement of the environment. It's just a per instance sample path guarantee. I do think, if we think of applying this in scheduling, one could, for example, apply this in, single server scheduling in a stochastic world where maybe you have uncertainty in the predictions of sizes, and you want to have, an algorithm that uses the predictions of the sizes, but, doesn't get messed up if the predictions are wrong, and still does well even if the predictions are wrong. So it doesn't shoot itself in the foot by using those predictions. And one could imagine a lot of these sort of classical resource allocation questions being viewed in this light, where if some job is coming 5 minutes from now that has a particular size, maybe that impacts your decision now, but you could be wrong about that prediction and you want to make a decision now that's robust to prediction error, but still good if your prediction is correct.
Thank you.
Yeah. Great. I guess we're probably way over at this point, so I guess we should stop. Thank you for all the questions. It was really fun for me to get the talk here. And please follow up with me if you have any more questions, or you want to chat, or you just have ideas about our papers or ideas of what might be interesting to look at next. Happy to hear them.
All right. Thank you, Adam.